Okay. So we're sticking with statistics. We're talking about different ways to characterize data. So something that we use in statistics a lot, measures of central tendency. What that means are there are different ways to characterize the center of your data, and that's what we're going to explore today. The first type of way that you can identify the center of your data is the mean. Another word for mean is average. And so the way we calculate average, if we're dealing with a sample, so we call that a sample mean when we're taking the average of the sample, the symbol for that is X bar. You see this bar on top of the X? Trying to highlight it. I don't want you to ignore that. X bar means sample mean, the mean from a sample. Population mean is this symbol, looks like a cursive U. It's actually a Greek letter called mu. That's the population mean. Again, taking the average from a population. The formula for the mean, I wrote it out in words. It's the sum of the values divided by the total number of values there are. And symbolically, the way we would say that is this symbol right here. It kind of looks like an E. It's, again, a Greek letter called sigma. You use that notation when you want to sum a bunch of values, when you want to add several values. X represents an individual data value. So to find the mean, you're summing each individual data value and dividing by n means the total number of values there are. So that is just symbolically a way to denote that, the mean. Again, a mean is just another way to measure your center. It's the average. Now, one thing we want to note about the mean, because to calculate mean, you have to sum all the individual data values, there may be data values that are extreme, meaning extremely high or extremely low compared to the majority of your data. Those are called outliers, and we'll talk about that a little bit later in the section. So when we want to take into account each score, it is good to use the mean. However, the mean is sensitive to each score, meaning your mean will be affected if you have extreme values in your set, in your data. Also with the mean, you want to round to one more decimal place. That's just the general rule. So if all of our data's whole numbers, we would round the mean to the 10th place. You just always round one more than your original data set. Next, we want to talk about the median. The median is another measure of center, but the median is essentially the middle number, but you have to put your data number in order. That's what ranked means. You want to order the data from lowest to highest, and then you find the middle number. That middle number is the median. And a very important point is that the median is useful when you don't want extreme values to affect. MCT means your measure of central tendency, your measure of center. You see, and we'll see an example of this, the median is not affected by extreme values because the median is simply the middle number. Whereas the mean we just discussed is affected by extreme values because look at the formula of the mean. You're summing all the values, including extreme values. That is the difference between the two. They are both measures of center, but one is affected by extreme values and the other, which is the median, is not affected by extreme values. And the last measure of center that we'll talk about is the mode. If you had to describe the mode briefly, it would be the number that occurs most often. The number or object depends on what you're looking at, but whatever occurs the most is the mode. There is an option where you can have no mode. meaning each object or number occurs just as many times as the other, there would be no mode. And you can have multimodal sets, meaning you can have more than one mode. So let's look at this first example and see if we can answer. It says determine the mean, median, and mode. Round your answer to the nearest tenth. Okay, so to find the mean, let's write that here. We are summing all the data values and dividing by the total amount of values. So I'm adding all the data values. And you will divide that by the total number of data values there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values there. That is how you find the mean. So summing all these data values, you get 501 on top divided by 10. And when you divide that, that is 50.1. Remember, you want to round to the nearest tenth. That is how you find the mean. In other words, I could say this is X bar. Remember, X bar is the notation for sample mean, the mean from a sample. Let's look at the median. The median is a middle number, but the most important thing is you have to put the data in order first. In the notes, I say you have to rank the data. That means putting the data in order. So I typically go from small to large. So we would start at 4. And what I like to do is kind of cross out as I go. That might be easier for you to tally which numbers, keep track of which numbers you've used. Then 6, then 8, then 9. Then there's 2 10s. Then there's a 12, 37, 40, and then 365. Okay, from there, what you do is you look for the middlemost number. So when I look at this, I know a value is in the middle because the numbers to the right would be the same amount of numbers to the left. But here, there are 2 numbers in the middle. You see these 2 10s, now to the left of those 2 10s are 4 numbers, and to the right of those 2 10s are 4 numbers. So when you have an even amount of numbers, you won't have one middle number. You're going to have 2 numbers in the middle, like how we have here. And so what you do in this scenario is you just take the average of those 2 middle numbers. That's what you do. And so 10 plus 10 is 20, divided by 2 is 10. My median is 10. And then the mode. The mode is the number that occurs most often. So let me take off the lines I put through the numbers. And if you look at the mode, the number that occurs most often is 10. 10 occurs twice, so the mode would be 10. I also want to point out one thing here. Based on this data set here, I'm sure we can all see that 365 is an outlier. It's an extremely high value compared to the majority of the data there. And so I want to point out to you guys how when there is an outlier in your data, it will affect the mean. Notice what the value of the mean is, 50.1. But look at the other measures of center. The median is 10, and so is the mode. Median and mode are not affected by outliers. That's what we saw above in our notes. And you see here, because when you find the mean, you're adding all the data values, including that extreme value, 365. That is why the mean is affected. It is drastically higher than the median or mode would be. Let's look at B. So for B, again, the directions are find the mean, median, and mode. So we'll go directly into finding the mean. I just want to bring your attention to this 48 is here too. These are all data, 48 followed by 52, 55, and so forth. I just don't want you to ignore the 48. So to find the mean, we add all the data values. And then we divide by the total amount of values there are. And if I count that, that's 12 numbers there. So the numerator, when you sum these values, you should get 547 divided by 12. And when you divide that on the calculator, you should be getting 45.6. That would be your mean. Your median is the middle value. But first, you have to put the values in order. So when we do that, we should have 39, oh, no, 35, then 39, then 40, followed by 42, 45, 40, oops, sorry guys, I missed one. After 42 was 43, then 45, then 46. Don't forget this 48 here, 50, 52, 52, there's two of those, followed by 55. Okay, so we've put the data in order. And now we're looking for the middle number, but keep in mind here, there are 12 numbers here. When you have an even number of, or a list with an even number, you're going to have to get the two most middle numbers. So the two most middle numbers here would be 45 and 46, because if you look to the right, there's 5 numbers to the right and to the left. And what you do is you take the average of those two numbers, meaning I add those two numbers and divide by the total amount of numbers here, which is 2. And when you do that, you should get 45.5. That would be your median. For your mode here, let's erase this. So the mode is the number that occurs most often. So if you look at this, the number that occurs most often here would be 52. 52 occurs more than any other number, so that is my mode. Now I want to provide an example, another example. Let's say I added to this list 55, just another number. Now, notice that 52 occurs twice, and also 55 would occur twice. If that happens, then your mode would be 52 and 55, because those two numbers occur with greater frequency, with the same number of frequency than any of the other numbers. And that would be considered bimodal. You would have two modes there. For C, I think we're okay with finding the mean and median, but I just want to go over the mode here. Mode is the number that occurs most often. And so if you look at these data values, there is no number that occurs more than any other number, right? Every number occurs uniquely once. So in this case, there would be no mode. This is an example of no mode. Let's look at example 5. It says, decide whether you expect the mean, median, or mode to give the best representation of center of the distribution and explain. So age at graduation for college students in the US. So we're being asked to determine what's the best measure of center. We know the mean, median, and mode are different ways we can measure the center. But sometimes there's the better representation, and it's based on what you're looking for. So in this case, we're looking for the ages at a graduation for college students in the US. So when I think about that context, in college, there's a variety of different types of people that graduate. There's traditional students, right, that graduated high school. And so they're probably around 21, 22 when they graduate college. There's dual enrolled students, right? So they might be 17 or 18 when they graduate college. And then there's non-traditional students, maybe people that have been in the workforce for several years and then went back to school at an older age. So because there's so much variety, and that means there's room for outliers, extremely younger individuals, maybe 17, 18, and older individuals, maybe in their 50s, 60s or older, going back to college. Because we want to take those into account, we would have to take those into account. The median here would be the best representation of center. And the reason why is because the median is not affected by outliers. And we just described what some potential outliers could be, non-traditional students that are going back to college or dual enrolled students. And because that is common at a college graduation, you want a measure of center that best represents and would not be affected by those outliers, and that would be the median. The B, number of times people change jobs during their careers. This is similar to A. So if I was looking for the best measure of center here, again, my options are mean, median, or mode. Median would also be the best representation of center, because once again, when you're considering the number of times people change jobs, there is a greater potential for outliers here. There may be some people that stay with the same job for years or decades, but then there are a good portion of people that change their job every 3 to 5 years. So because there is a greater potential for outliers in this scenario, the median would once again be the best representation. Weights of individual oranges in a 5-pound bag. So when we're looking for individual values, we care about the individual weight of an orange. The only measure of center that considers all values is the mean. And furthermore, because the oranges are in a 5-pound bag, I expect the oranges not to have outliers here. So we'll say that the oranges are typically close in weight. Because they come from the same bag. And then scores on a very difficult test on which a perfect score is 200 points. So in this example, typically when you're looking at how students did on a test, again, you want to consider all students. That's the point, right? You want to consider how everybody did. So when the context is you need to take into consideration all values, all people, all objects, the mean is the best representation. All right, the mean reflects performance of all students. Example 6. The following statistics represents weekly salaries at the Midtown Construction Company. So we have the mean is 600. These are people's salaries. The median is 590 and the mode is 580. We are being asked, what is the most common salary? The key word here is most common. The only stat here, as far as mean, median, and mode, that represents most common is the mode. The mode is the number that occurs most often, right? In other words, most common. So the most common salary would be 580. What salary did half the employees' salaries surpass? The key word here is half. Median is the value there that is the middle value. If it's the middle value, what that means is exactly half are below that value and half are above that value. So if the median is the middle number, to answer this question, what salary did half the employees' salaries surpass, meaning above? Well, the median is 590, which means the middle number is 590. So half of the employees' salaries are above 590 and half are below 590. And C, if the company has 100 employees, what is the total weekly salary of all employees? Keyword here, all. The only measure of center that takes into account all values, in this case, all employees, is the mean. And so the answer to this, what is the total weekly salary of all employees? That would be 600. So we talked about outliers earlier. Outliers are extremely high or low values, right? And so it says, do outliers affect the mean? The answer to that is yes, because remember the formula to mean. The mean is the sum of all values divided by the total number of values. So yes, because I'm summing all the values, if the data set contains an outlier, the mean will be affected. Whereas for the median and the mode, remember the median is the middle number and the mode is just the number that occurs most often. An outlier, meaning an extremely high or low value, will not affect the median or mode. Those are not measures of center that take into account all data values. So it will not be affected if there is an extreme value in your list. Okay, I want to direct your attention to distributions. Another word for distributions is shape, the shape of your data. And so typically we can see the shape of a data when we put our data into like a bar graph. I wrote the word histogram here. Histogram means bar graph. So when you have a table or a graph, such as a bar graph, you can easily see the shape of the data. And so we can see that here. Notice here is my shape. If I were to draw like a curve or a line to represent this, we call this rectangular or uniform distribution. And then next to that, again, this is what that curve would look like, or it can look this way. This is called J-shaped distribution. And then you can also describe the shape of data by its modes. So this is called bimodal. Bimodal means there's two modes, or peaks. Peaks are mode. So if you see here, here's one peak, and here's another peak or mode. So this is why it's called bimodal. And then in this shape or distribution, there's only one peak. So that's why we would call it unimodal, just one. So these are just different ways you can describe the data. So you can describe it through its distribution or shape. You can also notice its symmetry or skewness. So when something is symmetrical, that means if you were to draw a line through the center, the left half and the right half would be mirror images of each other. And that's the case with A, B, and C here. If I draw this line, this side and this side are exactly the same. In other words, if I were to fold this graph about that line, every point would match up. So we call this symmetric. The distribution is symmetric. If you were to draw a straight line through the center and fold it, each side would match. That is symmetric. And then skewed. A skewed distribution means the majority of the data is on one side. And so we say it's skewed, but then we go a step further and say what direction it's skewed in. And so take a look at this first graph. The majority of the data is on the right side here, right? This shows the majority of the data. However, the left side has this longer tail. We call this a left tail. And so whatever side has the longer tail, that's how you would describe it. So we say this is skewed to the left, or left skewed. Look at the next graph. We know it's skewed because the majority of the data is on one side, but to describe it, you look at the tail. This has a longer right tail, so we would say this is skewed to the right. And then we covered this above. This is symmetric. If we were to draw a line through the center, the left and the right side would be perfectly aligned, the same. So we have the definitions below. And then the last thing we discuss is variation. Variation essentially is how spread out the data is from the center. We're looking at how wide is my data set. So if you take a look at the next page, we have options of low variation, moderate, or high. And so for all of these, I'm looking at my center. So this is the center right here. I could call it X bar, right? The sample mean. The mean is a measure of center. And then you look at how wide it is from your center. We're here to here. Not very wide. It's not very spread from the center, so we would call it low variation. Whereas here's our center once again. And it ranges from here to here. It's a little bit more spread out, the data, but not too high, so we would call it moderate, not too far. And then here is our center. And you see here, there's quite a bit of distance from the center. So we would call this high variation. There's a big spread. So with that, let's look at number 9. Number 9 kind of touches on 7 and 8. So I'd like to do this example. So let's look at example 9. For each histogram, draw a smooth curve that captures its important features. So when I say draw a smooth curve, this is what I mean. We're drawing a curve to represent. Then classify the distribution according to its number of peaks, its symmetry or skewness, and variation. So the histogram below shows the F scale measurement of 490 tornadoes from recent years. The F scale runs from 0 to 5. So notice the horizontal scale goes from 0 to 5. And a high number indicates a stronger tornado. So we've just drawn a smooth curve to represent this. And now we want to know the number of peaks. Well, there's only one peak here. Remember, the peak is like your high point. There's only one. Symmetry or skewness. Well, symmetrical would mean if I drew a line on the center. So let's see. If I drew a line on the center, the left and right sides would match up. That's not the case here. I do see the majority of the data is on one side, so this indicates to me that there's some skewness here. And how do I figure what direction it's skewed? Whichever side has the longer tail. So if you see here, this right side kind of extends like that. So we would say this is skewed to the right. It has a longer right tail. And then variation, based off of the center, there is, I would say, moderate variation. The spread is moderate. It's not low, it's not very close to the center, and it's not high. We would say this is moderate. Again, variation, you're just looking at how spread the data is. In B, the histogram below shows the digits drawn in California's daily 4 lottery. So in your horizontal scale, you have the digits 0 to 9, and then in the vertical scale, you have their frequency, how often they were drawn in the lottery. Now, as far as peak goes, we were asked to describe the peak. There is no one peak. You see, this distribution, if I were to draw this, this is like a curve that would represent that, like this. This is what we call rectangular or uniform. This is a uniform distribution. There is no one peak. It is uniform. This is, you can also refer to this as symmetric. And so because it's uniform and symmetric, there is very low variation here. There are no extreme differences in the frequencies. So we would say this is a low variation. And I'll write Y here. No extreme difference in frequencies. This will always be the case for uniform distribution. There will be very low variation. Let's look at the next example. We're discussing GPAs here. It says a student has completed the 15 credits in the table below during one semester. So for part A, we're going to be utilizing this table here. This table. Grades are weighted as follows. So an A is 4, An A minus is 3.7, B plus is 3.4, B is a 3, B minus is 2.7, C plus is 2.4, and C is a 2.0. Find the student's GPA for the semester. So to find GPA, there's a formula that I'm going to give you right here. It is the mean. GPA essentially is a mean. But the only difference is if you look at his classes, for example, statistics, he got an A, and we know that the value of an A from above right here is a 4. However, there's something called credits. Credits mean the weight of that A. You know from being students that an A in a 1-credit class and an A in a 4-credit class are different. If you get an A in a 4-credit class, that would increase your GPA more significantly than an A in a 1-credit class. So credits are considered the weight. I'm going to write that above or below here. Credit is seen as the weight. These values here are considered just the value, the point even. So to find the GPA, you are summing each value times the weight divided by the sum of the weights. I'm going to write above, X means value and W means weight or credit in this case. So to find the GPA here, let's look at the table here. The student got an A, so we know an A is 4 points, right? But it's in a 4-credit class. Plus, I have to sum this all. Plus, look at Eastern religions. The student got a B plus. The value of a B plus is a 3.4. You see that right here. So that is 3.4 times. The weight or credit is a 3. It says that on the table. Plus, okay, in French, the student got a C plus. The value of a C plus is 2.4, and that was in a 4-credit class. In geology, they got a B minus. A B minus is 2.7. And the weight is a 3. It's a 3-credit class. And then finally, in geology, the student got an A minus. That's a 3.7. And the credits was a 1. That is the sum of the value times its weight. Now I'm going to divide by the sum of the weights or the sum of the credits. You can either add these credits, or it tells you in the problem the student completed 15 credits. So we know this is 15. And so to get one number on the top, you would multiply. You can write it just like that on the top. You should get 47.6 divided by 15. And when you divide that, how you would round this is how you would round a GPA. GPAs are rounded to 2 decimal places. So this would be a 3.17. Let's look at part B. It says, what grade would the student need in French to raise her GPA over 3.5? So now let's direct our attention specifically to French. I'm going to highlight that, or I'll circle it. The question is, in order to get a GPA of over 3.5, what grade does the student need in French? If you look above here, what we just did right here is how you calculate the GPA. And so really, the class that I'm trying to figure out the grade is the one I got a C plus in, which is a 2.4. So this is the value I need to figure out. I'm going to replace the 2.4 with an X because I want to figure out the grade she needs for this 4-credit class. So essentially, everything else is going to stay the same except that 2.4. And now I know what my GPA needs to equal. It needs to equal 3.5. And so everything else is going to stay the same. She got an A in a 4-credit class, and A is worth 4 points, plus a B plus, which is a 3.4 in that 3-credit Eastern Religions class, plus I want to know what grade she needs in this 4-credit French class and keep everything else the same. And you're dividing by 15. So my goal here is to solve for X. Now I can clean up that numerator there. If I do that, I should get 38. So meaning 4 times 4 plus 3.4 times 3 plus 2.7 times 3 plus 3.7 times 1. If I do that, I get 38 plus 4x. Now, I want to solve, and I should put here divided by 15. I want to solve for x. In order to do that, I can say this is 3.5 over 1 and multiply diagonally. So multiply in this direction, 1 times 38 plus 4x is just 38 plus 4x. I'm going to do it over here. And then multiply diagonally in this direction, 3.5 times 15. If you multiply that, you should get 52.5. And now subtract 38 from both sides. You're going to get 4x equals 14.5 and divide both sides by 4. X equals 3.63. So the question is, what grade would the student need? Well, a 3.63 means she needs to get at least an A minus, because look at what an A minus is, 3.7. I just calculated what she needs to get a 3.5, but she wants over a 3.5. So she needs at least an A minus, because an A minus means 3.7. And if she put a 3.7 in there, we would get over 3.5. Let's look at the next one. Ryan is taking an advanced psychology class in which the midterm and final exams are worth 35% each, and the homework is worth 30% of the final grade. On a 100-point scale, his midterm exam score was 85.5. His homework average score was 94.1, and his final exam score was 88.5. On a 100-point scale, what is Ryan's overall average for the class? So here we have a class that consists of a midterm, which is 35%, a final, which is also 35%, and a homework, which is worth 30%. And then it's followed by what the average was on each of those, the midterm, final, and homework. So to calculate the score in the class, you just multiply what you got, your score, by how much it's worth. So let's start with the midterm. Ryan scored an 85.5 on the midterm, and it's worth 35%. We learned change 35% to a decimal. Plus, let's look at homework. Homework, the score was 94.1, and we know homework is worth 30%, so multiply by 0.30. And then finally, the final, his score was 88.5, and the final is also worth 35%, so multiply by 0.35. And you can multiply just like this on your calculator. You should get 89.13. That means that is the student's grade in the class. And with that, let's look at part B. Ryan was hoping to get an A in the class, which requires an overall score of 93.5 or higher. Could he have scored high enough on the final exam to get an A in the class? So now I'm going to use this equation, but now I know the grade he wants is a 93.5 or higher. And what's in question is, could he have scored higher on the final exam? Look at the score he currently has. I'm going to replace this with an X, and I'm going to determine what score could he have gotten in order for this to equal now 93.5. So I'm keeping the midterm the same, the homework the same, and I want to figure out, so that's why I'm putting an X, what does he need to get on the final in order to receive, so this must equal a 93.5. And so let's solve this for X. So I want to simplify this left-hand side. If I do that, I should get 58.155 plus 0.35x equals 93.5. I want to subtract 58.155 from both sides. And I should get 35.345 there. Divide both sides by 0.35. And you're getting approximately 101. Now, let's think about what this means. What this means is, in order for him to receive a 93.5 in the class, he needs to get 101 score on the final. And so the question is, could he have scored high enough to get the A, to get the 93.5? Well, we just found out you have to get a 101, but all of these scores are out of 100, meaning the highest you can get on the final is 100. And if that is the case, then it is not possible for him to get the 101, which in turn means he cannot get a 93.5 in the class.